All right, so let's just discuss this real fast, then we'll move on. First, you'll notice in maroon, the test is a week from yesterday. That should be plenty of time. We have another lab we'll do on Monday. And that was pretty interesting. I don't know. Some kids really liked the one they did yesterday. Hopefully you like the one tomorrow. Well, Monday. All right, so test in about a week. There really is no homework. There was no blue sheet. So as long as you did the Christmas assignment, you're rocking it. Today, during second hour, I'll put in your lab score. Almost everyone was here. For someone, that'll be their first score of the trimester. But anyway, you really did. So let's just review this because this comes from an AP test question in previous years. So in this lab, we were supposed to get theoretical yield, all right, or our accepted value is the non-fancy way of saying that, all right? And whenever we do this, we just use math to find stuff. That math was where we took the grams of mg, we converted that to moles of mg, which we then converted to moles of H2, which we then converted to milliliters of H2. Okay? So to go from grams to moles, we just took the grams and we took 24.3 grams per 1 mole, and that put it in moles. Are we okay with that? All right, then to go from moles of one thing to moles of another, hopefully you will remember that requires a balanced equation. Mg plus HCl to MgCl2 plus H2. Now, when you balance this out, the only thing you need is a 2 right there. The rest were 1s. So no one on their AP test would waste their time doing this as a picket fence because time is extremely valuable. They would hopefully notice that the amount of moles used of Mg is equal to the amount of moles of H2 produced, a 1-to-1 ratio. So this step, when you went to moles, you had your number, all right? Then the moles of H2 was the exact same number. You okay with that? All right? And then to solve for volume, we used Pivnert. And we solved for V, which is nRT over P. All right? So now we have V equal to this number. That was our N. And then our 0.0821. And then our T we used, I don't know, we'll round it to 295 of all the things that I heard. And then our pressure, I don't know, when you did the math, what did that end up to be? 1.0 something probably? All right, 1.015. And this math told us what the accepted value was, what it should have been based on just pure calculations. Okay? So whenever we just plug stuff in, that's accepted. Then we did the lab. We literally put Mg in HCl and it bubbled up hydrogen gas in our eudometer, and we found that volume, and that was our observed milliliters of H2. Okay? That's what life really gave us. And they're very rarely the same unless we have exact tools, 100% pure reagents, and we are very thorough. They're hardly ever the same value. Okay? The observed is always what you get when you do something that's involving the lab. Okay? And then the final thing to do was just your percent error. And that was your observed minus your accepted divided by accepted times 100. Okay. We okay with that? It's a very likely problem to see in your future. Because it's good at testing a few different things, but it doesn't take a half hour. Okay? So hopefully you're comfortable with that. If you need more help on what we really were doing in that lab, come to B time and we'll figure that out. Okay, the rest of the hour are these two things. IDGL, anyone know what that acronym stands for? Ideal gas law, okay, which is PIVNER. All right, so we're going to talk about density and molar mass from the ideal gas law, and that will be the lab on Monday. I'm going to give you a thing, and you're going to get some gas out of it, and you're going to use math to figure out what that gas is. It's a pretty cool lab. It hardly ever works perfect because it's just hard to make things perfect in a high school chemistry lab, but it works good enough. All right, and then we should get to partial pressure. So I think we actually did the first couple of slides of this. There's actually only two. So it should already sort of be in your notes, didn't we? Thanks, Kitzel, for nodding yes. All right. So I did this. So we can manipulate the density equation to enable us to find the molecular mass of a gas. That's why I'm out of order. It was right here. I think we ended here. And if you don't understand how we got here, that doesn't matter. What does matter is that you know that equation and how to use it. So density is equal to PM over RT. All right, now M, that's the molar mass of the substance. Now, what's pretty cool is typically we give you the density and then you find the molar mass. That's how we usually do these things. All right, so as long as we know these things, at least 4 of the 5 we can solve for the other one. R is a constant, so really it's 3 of the 4. Okay, now rearranging that, that's where this slide comes in. I realize I popped that out of order. So we can multiply the density equation, manipulate the density equation to enable us to find the molecular mass of the gas. So D equals PM over RT becomes M equals DRT over P. And this is the one, like if you're going to just commit it to memory, you're going to use this more than this. And it's fine. It's the same equation, just written in different orders. But I memorized this, and it will just sound stupid. I memorized it as dirt, P. And that sounds stupid, but I never forgot it. I still remember it, and I memorized it over 25 years ago. Dirt, P. Dirt was on top, P was on the bottom. All right? And so, like, if you can memorize this super easy things like that, these problems are not hard. They're just algebra. Okay? Now, I don't know. Did we do any of these samples? Okay, so let's work through these. What is the density of methane at 298 K and 1.05 ATM? Okay, we're just going to plug these things in. This one won't take to work that through. All right, so density is equal to P, which is 1.05. All right, CH4 is 16 grams, correct? All right, and you can put per mole, but if you've noticed, I've been super lazy on writing the units in the problem. That's for, like, on purpose. That's a waste of time. Just write the right unit in the answer. All right, R is 0.0821, and T was 298. You plug that in, and what did you get? Something louder, 0.69. All right, now, you have to be careful here. Piv nert, the volume was always in liters, and there is no volume here except for there is liters here. These are grams per liter. When you do the volume of the gas, it's not grams per milliliter, it's grams per liter. Okay? Okay? Not too bad, just plugging in, correct? All right, we'll make it a little worse. A sample of 27 grams of a simple hydrocarbon is found to occupy 2.8 liters at a pressure of that. What is the molar mass of this substance? What is the most likely formula of this hydrocarbon? Draw the hydrocarbon, and how many sigma bonds are in the hydrocarbon? Now, there's an important word in here that we have not used very often, or maybe at all, and it is this word right here. Simple. Simple hydrocarbon tells you there are no double bonds. If it's a simple hydrocarbon, it means it's a C, C, C in it. But there are no double bonds. You okay with that? That will help you with this entire problem. It is a simple hydrocarbon. Now, this is more like a 5 to 8 minute problem. So we'll pause that. Please try all of it. All right, so the first step is to find the molar mass using dirt. So the density was 27 over 2.8. I'm going to multiply that by R, 0.0821. I'm going to multiply that by the temperature. 32 ends up to be 305. All right, and I'm going to divide that by, where did I put it? Oh, 3.4. Okay. You plug all that in, and what did you end up with? 70.9 something? All right, so we'll just call it 71. And that is a pain. I was not perfect. I was off by 1, but whatever. We're going to call it 71. All right. Then, the next thing. So who was at least okay with that? That part good? Okay. All right. So now, what is the most likely formula of this hydrocarbon? There's a fairly easy way to figure this out. You take this number and you divide it by 12. Do you know why you divide it by 12? That's the mass of carbon, which is by a significant amount, the most massive part of the atom, right, or molecule. Get this. Post you had, it was like 5.8. All right, 5.8. When you do this, you go down to the nearest whole number. And that will tell you the number of C's involved. All right? Because if you go up, you still have to have all the hydrogens, and you'd be way over your value. Does that make sense? Okay. That tells us that this most likely has 5 C's. All right? We know it's a hydrocarbon, and it's a simple hydrocarbon, which means no double bonds. And this next piece, I've said it a few times, but it may not have resonated yet. To find this number, some of you may have just put an 11, because that gets you to 71. But that won't get you the right model, because it's not 71, or it's not 11. If it's a simple hydrocarbon, the number of H's is equal to 2N plus 2. And N is this number. 2 times the number of carbons plus 2. So this ends up to be C5H12. Okay? Now, I do know that gets you to 72, which is not exactly 71, but we're close. And the model of C5H11 will not work. So that's how it couldn't have been that. All right, so now we come up here. We have C, 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 C. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Every single one of them is a single bond. So we just count. We know we have 12 between the C's and H's, and then 1, 2, 3, 4. So we have 16 sigma bonds. You okay with that? Remember, every bond is a sigma bond. A double bond is a sigma bond and a pi bond. Okay. If this included a double bond, this question would be significantly harder. So usually won't. The only way it could, you would have to tell you it had that type of bond. Okay. I don't know. How about give me some feedback here? Time that we've discussed this. And from now on, this is where it really does matter. It hasn't really been required until we get into chapter 10. All right. And what you would call this is organic. Ooh, I hate this stuff. Well, this part's easy, but when you go to college and you take this, you're going to hate it. Well, that's all. This is all the organic we do the entire try, so don't stress. Yeah, organic nomenclature. All right. Now, it's just a language, and it's a huge language, but in this class we only have to learn like the tiniest sliver of all things. You need to know 3 ways that these end. An organic or a hydrocarbon, which is all we care about, because they are way more complicated than this. But for us, all we care about are basic hydrocarbons. They will always end with either the letters A-N-E, E-N-E, or Y-N-E. So we could have propane, propene, or propine, and the ending tells you what types of bonds you have in there. The prefix is just always the thing that tells you the number. So pro means 3. All right? And I think we went over that as well. And I'll go over it right after this slide. So if you have an alkane or a simple hydrocarbon, the formula is always CXH 2x plus 2. All right? This x right here is what will give us the prefix. All right? So if we have hexane, this x is what? Okay, 6. And then we would plug it in here. If it was ane, hexane would be C6H14. Hexane? Yeah, it's definitely a thing. I have some in the back room. It's an extremely good cleaner of things that water won't clean. It's the one solvent for nonpolar substances that we'll use. All right, ENE, so propene. The ene would tell me, hey, I have at least a double bond, which if I have a double bond, that reduces the amount of hydrogens by 2. So now it's X and H2 times X. We don't add 2 anymore because that took off a pair. The YNE, propine, we have a triple bond. All right, and now these extra, every time we add a bond, we remove a pair of hydrogen atoms that need to be there. So now we have 2x minus 2. Okay, so ANE means no multiple bonds. ENE means one double bond, at least. If there's more than one, the name gets really long. You don't have to know that, so it's going to be 1. And then we have one triple bond. Now, prefixes, I don't think I have these written. The prefixes, this is how I memorized it. You got to remember, I'm a weird memorizer, but it helped. M, E, P, B, then, oh, remember geometry. That's my jingle I made up to myself. And I don't know if you noticed, but when I said propane a second ago, like 2 minutes ago, there was a tiny little pause when I went to tell you how many C's there were. You know why? Because I had to say MEP. That's 3. All right. MEPB, then remember geometry. The first 4 don't make sense for anything you've ever learned in your life. But after that, just remember geometry. Like pentagon, hexagon, heptagon, octagon, nonodon, decadon, whatever. All right. But we're not going to get that high. We pretty much stop at octane. So, M is meth. All right? We could have methane. Yep, finally. Breaking Bad. All right? No, that meth, the drug, and meth, the prefix. All it means is meth has a CH3 functional group on it that must be the active site where the drug really matters. But it's a gigantic molecule, but it must have a CH3 hanging off the end of it. All right. So whatever. Then, so we have meth, we have eth, we have prop, and we have bute. Yeah, you've heard of butane. You've heard of propane. I don't know if you've heard of ethane. Methane is natural gas. It's what comes out of the Bunsen burners we light on fire. All right, ethanol. Now, ethanol ends with an OL, which means it's an alcohol. Yeah, there's 2 C's. And you can learn this whole language. It has 2 C's, and it has an OH on the end. That's what the all tells you. It's an alcohol. Then everything else would just be an H. Okay? It's a regular hydrocarbon with an alcohol group. Or we can call it a hydroxide group, but typically in organic we call it an alcohol. All right. Now, these then would have their endings. So butane, butene, and butyne. And I would know the front and the end from the name. Bute would tell me that I had C4. If it was ane, it would be 8 plus 2, so H10. Ene, I would still have C4, but it would be just 2X this time, so it would be H8. Butyne would be C4, H2X minus 2, so that would be a 6. Okay? It's a tiny bit tricky, but overall, MEPB, then remember geometry, then you'll be all right. And then the other thing is the ane, ene, and ine. There's your introduction to organic chemistry, and that's about it. Yes? In my opinion, of all of Chapter 10, the idea of partial pressure is the easiest. The math isn't that bad, but it's, I don't know, whatever. Partial pressure, the idea is that the total pressure of a mixture of gases equals the sum of the pressures that each would exert if it were present alone. This is something really weird, but I don't know that I still feel 100% good about it. But the pressure of a gas in a mixture has nothing to do at all with the pressure of any other gas in that mixture. They behave completely independent of each other. Yeah. That is bizarre. But it's okay. We can work on it. And whatever. So to find the total pressure, we just take P1, 2, 3, and add them together. It's very simple. It's like the money count is equal to my dollars, my $5, my 10s, my 20s. I don't have higher than that because I'm a teacher. I'm just kidding. I get paid a ton. Don't ever think I complain about how much I make. All right. But don't tell your parents I need a pay cut either. I'm comfortable. Okay? Now, Now, this is from a thing on my site, if you ever want to look at this. There's like a note, little guide. It's like 2 or 3 pages. You can look at it. It's on Canvas or BEHS Science. For this little part. So each gas in a mixture of gases behaves independently of the other gases present. Therefore, each gas in the mixture obeys the ideal gas law. Treat each of these gases separately in the mixture. For questions, that's funny, that says 4. Oh, it is supposed to be 4, sorry. 4 equations, I can't read it all. 4 equations govern the treatment of partial pressure equations. First, Dalton's law, which is what we just wrote. The total equals the sum of all pressures. So you just add them together. Mole fraction, which is X, or that like Latin-looking X that we have. All right, that's the mole ratio or mole fraction. It's the moles of individual gas divided by the total moles in a mixture. Okay? And just a simple example of that, if we wanted to know the ratio of girls in here versus boys, you just take the number of girls divided by the total number of people. Okay, that's all you're doing. Don't let the word moles blow your mind. And then the ideal gas equation, which is PV equals nRT, and then the partial pressure. And we went over this, and it was one. The pressure of is equal to its mole fraction multiplied by the total pressure. Okay? The pressure of 1 is equal to its mole ratio times its total pressure. All right, anytime a mixture is given in the problem, you will need to use these equations to solve. Here's an example. I think it's on the next page, but I'll cut and paste it here. I don't know how easy that'll be. Let's see here. Yeah, that won't be too hard. We'll see. Here we go. That way you can still have that if you still need it and you have the problem. Mixture of 9 grams of oxygen, 18 grams of argon, and 25 grams of carbon dioxide exert a pressure of 2.54. Okay, so all 3 of them. Is this the exact one we did on the video? Okay. The pressure is 2.54. That's the total pressure. All right. Initial pressure of each gas. Okay. Apply these. To find the mole fraction, you're going to have to find the moles of all of these. I will save you some time. Oxygen is 32 grams per mole. Argon is 40, right? What's that? Oh. And carbon dioxide is 44. Okay. Oh, that was cute. All right. Uh-oh. No, we're good. All right. Trying to follow my own process of writing here. Looks not terrible. All right, so the first thing I did was I divided each by their molar mass. That was to find their moles. Okay, so that's step 1. Convert each individual part to moles. So divided by 32, divided by 40, divided by 44. Then, the next step that I did is I added all 3 of the values to get this, the total moles. Because my mole fraction, it is the mole of 1 divided by the total moles. Okay. So once I added, then I had the denominator. 1.3 was the total, and I had it 3 different times. All right, so the next step was to divide to find the mole ratio, which was X. I did that, 2.81 divided by 1.3, repeated that each time. All right, now, this gave me this value was your mole ratio. Okay, it was the fraction of moles of oxygen to the total. I did that for each one. Mole ratio right here. And I multiplied each one by the total pressure to find out how much one was contributing to the whole. And I get 0.54, 0.89, and 1.1. Okay, there are 2 checks along the way to know that you're doing it right. Brinley pointed out that these numbers right here should add to 1. Your mole ratios, they must always add to 1, or like 0.99 or 1.01. Like they better be dang close to 1 or you did some math wrong. And then, this one's obvious. If these don't add up to 2.54, then you have a big problem. Okay? So there's 2 ways to check